Our next speaker is Joao Marques-Silva. He's going to talk about formal reasoning methods in machine learning explainability. So Joao Marques-Silva is a research director at CNRS at IRIT in Toulouse in France. He's very well known for developing the core technology for CDCL solvers that are everywhere in SAT solving these days, and not only in SAT solving, but also in automated reasoning tools and well beyond NP. I mean, the problems well beyond NP. And he's also known for pushing the state of the art in solving max out problems and related problems, essentially tackling with over-constrained systems. And more recently, he pushed the state of the art and made significant contributions in logic-based explainable AI. So, Joao, please start. You are starting a bit later, so I think we will be able to use a couple of minutes afterwards because we have a break.
Okay, thank you very much. Do I have share privileges?
Yes, you should.
Yes. Okay. Thank you very much. Good afternoon, everyone. Thank you for attending my lecture, my talk. I'm going to talk about how to apply different types of automated reasoning techniques in explainable AI. So again, as Alexey was kind enough to explain, this is a fairly recent area. So if you have comments, those will be most welcome. Okay, so everybody's familiar with the successes of machine learning, from self-driving cars, social robots, image and speech recognition, personal assistants, Watson, and more recently the many successes of DeepMind. So there is a huge expectation with respect to machine learning. At the same time, people now accept that machine learning models are brittle, meaning fragile, and a very well-known example are adversarial examples. So I think this was the first example of an adversarial example. You have a picture of a panda, and it was classified correctly by a neural network as a panda. You put a little bit of noise on top of the image, and the classifier now says it's a given, even though for us human beings, it's still a panda. And after this first result in 2014-15, different results have been shown how neural networks can be brittle. So for example, if you put some dirt on a stop signal, it will be classified in a specific neural network as speed limit 45. And another one, you blur the image, you get speed limit 80 miles per hour, and so on. And what people essentially these days agree is that depending, of course, on the neural network that you are considering, you can do pretty much everything that you want. So here is the standard example of a pig. You put some noise on top of the pig, and you have an airplane. And so that is, again, there are lots of more examples like this one. A somewhat more problematic example or more serious example is this one. So you have the original images, the picture of a tumor, which in this case would be classified as benign. If you put a small amount of noise on top of this image, and for us, again, it's the same image almost, it will be classified as malignant. And of course, we can flip the images, and so this shows possibilities of doing pretty bad things with neural networks. So this is one aspect. The other aspect is that some machine learning models are deemed interpretable by different researchers, and those are decision trees, decision lists, rule lists, decision sets. I have here two examples. So a decision set, it's a bunch of unordered rules, and a decision tree for a very simple example. Okay, and so this is something that people in general would consider interpretable. And then you have models that pretty much everyone agrees they are not interpretable, like a neural network. So you have an image of a cat, a neural network, and you correctly predict it's a cat. But essentially, we don't know why the neural network is predicting the cat. So we don't know which features are important. We don't know if there are general explanations for why this is a cat. And a few years ago, in 2016, DARPA proposed the acronym Explainable AI, and the objective at the time was, given a black box machine learning model, we would like to be able to do more than just being able to classify correctly, which was what could be done at the time. So we would like to be able to provide some sort of explanation for why the machine learning is doing correctly its prediction. There are, since then, and around, actually in Europe at around that time, GDPR, so General Data Protection Regulation, was approved. Some authors believe that the GDPR entitles people in Europe to the right to explanation. As I said, DARPA proposed the XAI research theme. There was a proposal for an algorithmic accountability act in the US. And some authors, well-known authors, have essentially justified why we need explainability to trust machine learning systems that can have an impact on what in our lives, essentially. And more recently, 2 years ago, the high-level expert group in AI proposed guidelines for trustworthy AI. And among several recommendations, there was the principle of explicability, which essentially justifies the need, again, to build trust on AI systems, the need to explain what the predictions that machine learning models and systems do. And of course, when I wrote these slides, there were hundreds of papers. Now there are thousands of papers on XAI. So what we have been doing for the last 2 years is we have a chair in ANITI in Toulouse, and what we are doing is applying formal methods in different areas of machine learning, and at the intersection of machine learning and formal methods. So explanations, fairness, learning, and robustness. And most of the work until now has been on explanation. So we started by understanding what the rigorous explanation was, how could we compute the rigorous explanations, assessing the quality of heuristic explanations, and I'm going to talk a little bit about that, and developing techniques to be efficient in computing explanations, and I'm going to talk a little bit about that as well. So here you'll have a bunch of publications that we have on this topic. We also worked on learning models that respect some specific properties, for example, size, but it could be fairness or robustness. And we also worked on fairness. We have a first paper on applying formal methods in fairness, and another topic in deep level is robustness. So we have a number of questions we would like to address in robustness. Okay, having said that, we can now move to the core of the talk. So the talk has two parts. First, I will give a little bit overview so that people with more background in constraints are familiar with the way we attack these problems. And then I'll go over the work we have been doing in explainability. So this summarizes the key ideas of this talk. So let's talk about, so first let's define what we mean by classification problems in machine learning, then a little bit of logic and how we encode different types of machine learning models with logic. So we are going to assume a set of features, that each feature takes value from a specific domain. We don't, at the outset, features can be categorical or ordinal or discrete or real value, no restrictions. And we define the feature space by using the domains of each feature. And each machine learning model for us just computes a function from a feature space to a bunch of classes, a set of classes. For simplicity in this talk, I will either use plus and minus or 0 and 1. An instance is a point in feature space and the associated prediction. And I will use a sample point instance, just all these possible names. And when necessary, I will view a point in feature space as a set of literals equating a variable associated with a feature with a concrete value, specific value, constant value from the domain of that feature. And if the features are Boolean, I will just use not xi for when the feature takes value 0 and xi when the feature takes value 1. Okay, so when we talk about explainability, a very important topic is being able to understand entailment. So let me see if we are all on the same page. So Let's assume we have a formula which is computing a function. We use the same name just for simplicity that maps some feature space to 0, 1. And suppose you have some other formula, tau, also defined on feature space, computing again a Boolean function. So we say that the second formula, tau, entails the first formula, phi, and this is the notation that we use, tau entails phi, if for any point in feature space, whenever the second formula, tau, is true, then phi is also true. And we can actually, we can double negate this, so we get not exists and then negate what's inside, and then we can observe that essentially not exists next such this is true, essentially corresponds to not satisfying this. And essentially this allows us to decide this first problem with a call to an NP or a SAT oracle or CP oracle as you wish. Now let's see an example. The feature space 0, 1, 2 dimensions. So we have a classifier defined on 2 features, x1 and x2, and so x1 or not x2. Clearly, x1 entails phi. Why? Because whenever x1 is true, for sure the function is going to be true. The same way, not x2 entails phi, because again, when not x2 is true, the function is going to be true. A more complicated example defined on 3 features. And as you can see, so it's a disjunction of 2 conjunctions. So x1 and x2 certainly entails. Whenever x1 and x2 is true, then for sure the function is going to be true, and x1 and x3 also entails the function. Okay. If for some reason we have a non-Boolean classifiers, and of course in machine learning most often we have non-Boolean classifiers, this is not a problem. We just create a form, a modified form, which is a predicate whether the classifier takes value C or C some class. And clearly, so this function now takes value in 0, 1. So when we talk about explainability, I'm going to talk about prime implicant. So let's see also whether, to clarify the definition of prime implicant, a conjunction of literals pi, which we can also view as a set of literals, is a prime implicant of some function if the set of literals entails the function, and any subset of that set of literals does not entail the function. So for example, going back to the previous example I showed, so here for sure x1 and x2, as I explained before, it tells the function. So whenever this is true, for sure the function is going to be true. But any subset, so either x1 or x2, does not entail the function. So we could have x1 equals 1, for example, and if I put x2 equals 0 and x3 equals 0, then the function is not true. So there is no entailment there. So let's see how we can represent machine learning models with logic. Well, first example is a very simple classifier. So I have 2 features, x1 and x2, taking values in 0 and 2. So we can view them as integer. And I have 2 rules, an order. So if 2x1 plus x2 greater than 0, I predict plus. If 2x1 minus x2 less than or equal to 0, I predict minus. So a fair question is whether the model can predict both plus and minus at the same time. So is there a point in feature space where we are going to predict both plus and minus? So how can I find this? So in this case, actually, if I think about it for some time, it's clear that this can happen. If I put 1 here, so it's 2, 2. And then, sorry, if I put 0, it's 0, 0. If I put x2 equals 1 here, it's 1, greater than 0, minus 1, less than or equal to 0. So I'm going to predict both, plus and minus. So I can formulate this as follows. I have a Boolean variable which is true whenever the first condition is true. And I have a second variable which is true if and only if the second condition is true. And what I want is the first and the second to be true at the same time. Now, since this is not purely propositional, now I could of course encode this as propositional, but since in this case it's not purely propositional, I can just use I could use a CT solver or an SMT solver, which in this case would be easier. And so there is a model if there is a point in feature space where I have both predictions. A more complicated example. So in this case, again, I have an ordered rules, 3 different rules. All of them are Boolean to keep things simple. And I have 1 rule to predict plus and 2 rules to predict minus. So again, I can ask, for example, the same question. Can I predict plus and minus both at the same time for some point in feature space? And again, if you think about it, the answer is yes. We have 4 points 0.1011, and if you plug in the values, so 1011, so this is false, but with 11 this is true, and that one is also true, so I'm going to predict plus and minus. And so in this case, I can also represent the problem, in this case, in pure propositional logic. So I pick the first positive rule, and the first, in this case, the only one, if this condition is true, if and only if this condition is true. I pick negative if this, the first negative if and only if this condition is true. I pick the second negative if and only if this condition is true. And I pick positive if I can only pick the first positive. I pick negative if I pick the first or the second negative, and I want to pick both positive and negative. Of course, I could simplify this. This is just illustrate how you can automate the process. And so again, I think it's clear that we can model all these types of problems with logic. A natural question is, okay, this is fine. How do we do neural networks, right? So the next step, of course, is let's see how we can represent neural networks with in this case, mixed integer linear programming. Okay, so we are going to view each layer of the neural network as a block, except the first one. And what happens is that, so this blue circle is going to do the following. We compute first intermediate value x prime, given x and the weight matrix and some bias. And then what we are going to do is compute the outputs given intermediate value and some activation function. So we are going to describe how this can be done with the ReLU activation function, which is, again, as shown in the previous talk, is widely used. And so this is how we view the ReLU activation function. So essentially what I just said is as follows. We compute an intermediate value, which is a dot x plus the bias vector. And then I take the max of the intermediate values with 0. So this is my ReLU. And so how can I encode each block? So again, this is can be viewed for each node as a summation. So the different weights, the input variables, and the bias. And this summation can be positive or negative. So what I'm going to do is I'm going to represent this summation as the difference between two positive variables, yi and si. And this works like this. If the summation is positive, I'm going to put the value in the output. If this summation is negative, I'm going to put it in what is called the slack variable. So I'm going to put it here so that I cancel the value and yi is set to 0. So I make sure that I use a Boolean variable such that only one of these, yi and si, can be greater than 0. And this way I'm ensuring, because they are both positive, that one of them is going to be 0. And so this way, either one or the other is 0. And in order to have equality, since both are positive, so if this is positive, then it's equal to yi. If it's negative, I equal to the complement of si. There are simpler encodings, but they have been shown not to be as effective. So usually people ask lots of questions about this. And so the first comment I'd like to make is that, so this I hope convinces most of you that it's easy to model machine learning models with logic. And usually it's simple. Let me show you a concrete example. So suppose it's a really simple example, just to illustrate the point, again, using the ideas in the previous slide. So we have a classifier, which is, to keep it very simple, just two features, and it's a disjunction. Both of the features are Boolean, so I can only have 0 or 1. And I'd like to model this classifier with a neural network. So one way to do it is I'm going to use two layers. The first layer, I'm going to compute ReLU of the matrix of weights times the inputs plus some bias. And this is the matrix of weights is this one here, and the bias is this one here. So the two values that I'm interested in are ReLU of this. And again, so how do I compute this? So again, notice that since I have 1, 1 given x1 and x2, it's going to be x1 plus x2. Right? And the second one, it's this one, x1 plus x2, and of course here it should be 0 and minus 1, I'm sorry. So it should be 0 and minus 1. But again, so the point actually is the encoding itself. And so So as you can see, what I'm going to do, what I'm doing here is using this, what I showed in the previous slide. So how do I do y1 and y2? Essentially, I equate the sum with the difference between two variables, and I equate this sum with the difference between two variables such that if the sum is positive, it's going to be equal to y1, and if it's negative, it's going to be equal to minus s1. Okay, and the second one, I don't use bias. I'm computing, so value, it's, again, I just have y1 and y2, so it's going to be y1 minus y2. I take the max over 0, and I'm going to compute an output, which is a 1, which can be either then greater than 0, which means I'm predicting 1, or a 0, and this means I'm predicting 0. So in this case, this is the additional constraints I need for this part are shown here, and Z3, and then a 1 here. Okay. So again, I hope this is clear. So you can, of course, if you have a much more complicated network, you can just automate this. So let's talk a little bit about explainability. So I'm going to cover a bunch of topics. So first, let's see how in general we can compute explanations. So to keep things simple, I'm going to assume that the features now are categorical. Again, I have feature space. I'm going to use just two classes as I suggested before. And when I have some instance, the prediction is essentially computing the value of the classification function on the point. And I'm going to view each point in feature space, as I suggested before as well, as a cube, so a set of a conjunction of literals, where the variable associated with the feature takes is either equal or not to the value, to the constant value specified by the point in feature space. So what do we have? The way we started is as follows. We have an input, which we represent as C. It's the cube conjunction of literals. We have, for example, a neural network. So it's our M. The encoding of the neural network is our M. And we can use any type of encoding, SAT, SMT, constant programming, etc. And then the output in this case would be just, it's a cat. So it's a literal, which is essentially says, well, I'm predicting a cat. So we know for sure that if I have the input cube and the model then for the neural network, this entails the prediction cat. And we can look at this in terms of positional reduction. So I have a bunch of hypotheses. So all the literals in my input, I have a theory which represents my neural network, and I have a manifestation, which is what I see at the output. And I want to find a subset of the input cube, so a subset of literals from the input, such that I'm consistent with the model, and what I pick and the theory is consistent with the prediction. So and there are a few observations that we can make. This is, of course, must be a tautology because it's a subset of the inputs and applied to the model. So it's certainly consistent. I can transform this entailment shown here as follows. So I wanted the set of literals that I'm picking to entail M implies the output literal. And so if I do this, then the set of literals that I'm picking is a prime implicant of this function. M implies the output literal. So, and this means that we can, we equate explanations with prime implicants, number one. And what we need to do now is compute, we can either compute subset minimal or cardinality minimal prime implicants. And so, so this is what we call explanations. Not only us, different groups are now calling these explanations. And it's a very strong statement because we are saying that for any instance that is consistent with the set of literals that I'm picking, given the model, I'm guaranteed to have the prediction. Okay. So if we want to pick a subset minimal explanation, this is how we do it in general. So it's a trivial algorithm. It has been around for at least since the early 90s. So essentially go through the literals of my input cube. And if I have entailment, if I take the literal, then I take it and I proceed. So this is guaranteed to give me a subset minimal prime. It's not guaranteed to give me the smallest prime. If I want the smallest prime, the problem is usually harder. By the way, this reduced, for those of you familiar with the term 2MUS extraction, I'm going to explain what this means shortly. If I want the smallest cardinality minimal prime or a smallest prime, we use what is called implicit eating set utilization. So this is, I still have a loop, but the loop may be executed an exponentially large number of times. So I may have an exponentially large number of checks to entailment. And each time I'm computing a minimum meeting set, which again, it's a bunch of calls to an NP oracle. And so this can be much less efficient than the previous approach. But this is guaranteed to give you the smallest time. So what have we done? We are looking at subset minimal sufficient conditions for the prediction. So essentially what we are doing, and others are doing as well, several groups now, equating explanations with prime implicants. So what we do essentially is pick a subset of the input literals such that this statement, this first order statement is true. So for any point in feature space, if the set of literals that I pick is true, then the prediction is guaranteed to be what I'm looking for. As I said, other groups have proposed equating explanations with prime implicants with a different setup in terms of the algorithms used, but it's exactly the same definition. So, how do we compute in practice PI exponentials? So again, this is the form that we are interested in guaranteeing that is true, and I want to find a subset such that the form is still true. So for this form to be true, this one must be false. So I talked about this a few slides back. And so this means that this part here has to be unsatisfied. And what I do now is, well, this I cannot change. This is my model. So we call them the hard constraints. This has to be satisfied. And the soft constraints is what I can be flexible about. And so I want to find a minimal subset of the soft constraints such that this is still unsatisfiable. So this means corresponds to a MUS extraction. So it's known that finding an MUS is SP to NP. This means I can solve the problem with a linear number of calls to an NP oracle in the worst case. And finding the smallest MUS is in FP to sigma 2P, which there is completeness for CNF formulas. In general, it's open. So it's a much harder problem. So again, if you recall, this is how I talked about encoding the neural network, and this was the encoding that we proposed. So and this is for that example I showed before, encoding the mixed integer linear programming encoding for this classifier. Now let's do a little bit of reasoning about this. So for suppose the instance is 1, 0. So if it's 1, 0, I'm going to predict for sure 1. Okay. And this can be schematically can be shown here. So what I did, this is the assignment, one satisfying assignment, and this shows this constraint simplified just with the values that I'm assigning to the variables. Again, we can check this, but it's easy to see it's correct. So I want to compute an AXP, so an objective explanation or a PI explanation, so a prime implicant given the set of features 1, 2. Okay. So let's see what happens if the first thing is, the question is, okay, can I get rid of feature 1? So an easy way to do this is, can I flip the value of x1 from 1 to 0? And here we see that this is, well, of course, I need to keep the prediction. And as you can see, if I call the reasoner, in this case, the MLP reasoner or SMT reasoner, it's going to tell me that the output is 0. And again, this illustrates, in this case, I'm illustrating why I need a slack variable, because again, the summation is negative. And so I'm going to put the negative value in the slack variable. So this means I cannot get rid of the feature 1. So I need to keep it in my explanation. So x1 must be 1. So since it must be 1, I can ask, okay, can I now flip the second variable? And so I'm asking, can I flip and still get the output 1? And as you can see, again, we're plugging in the values here in the model. In this case, we see that, yes, it is consistent and the output is 1. So this means that the value of x2 is actually relevant for the prediction, and it's clear if x1 is 1, I don't care about the value of x2. And so I can drop the feature, and I can say that an explanation for this prediction is just the first feature. So I'm saying that for all points in feature space, again, in this case, it's Boolean, but it does not have to be Boolean. If x1 is true, which is my explanation, then the prediction is what I want. Okay. So we implemented this in 2 years ago in 2019, and we got some results, subset minimal and cardinality minimal explanations for these are different data sets, number of features. And these are the explanations that we computed, smallest, average, and minimum. And we used SMT solvers and mixed integer linear programming solvers, and several conclusions we observed at the time. So first, a huge misconception that I've come across many times is that people usually say, well, we need the smallest because it's much smaller. So yes, theoretically it's much smaller. In practice, I've never seen that. So as you can see here, when we can compute the explanation, the smallest explanation is not very far away from a subset minimal explanation. Notice that here we don't even do any bytes, we just compute one of them, okay? So number one. Number two is that for this type of problems, for neural networks, mixed integer linear programming solvers are more efficient than SMT solvers. This was the case 2 years ago. I presume this is still the case. And then what we also concluded, as I motivated before, is that finding the smallest explanation is much, much harder than finding just a subset minimal explanation. And this explains why it's important to find a subset minimal explanation and probably not the smallest or cardinality minimum explanation. Okay, so to the best of my knowledge, this was the first rigorous approach for explaining neural networks. So that's the good news. The bad news was that we could scale this to a few tens of millions. Okay, and we have not, again, I think we can improve it a little bit, but I don't think right now we don't have yet the technology to do large scale neural networks. Again, of course, this is a huge research challenge. Let me tell you what we have been doing. So the first thing we did was to evaluate heuristic explainers that have been around and are extremely successful. So there are several. There is Lime, Sharp, Anchor, among a large number of heuristic explainers. And so the question we asked was, okay, are these any good? Can we trust these explanations if we are going to use this in situations that are high risk? And so very briefly, for those of you that might not be familiar, Lime and Sharp, they don't really compute explanations. They compute a simpler model, which they say it's the explanation. So they compute a simpler interpretable machine learning model, a linear classifier, a decision tree, and so on. They are very different from the way they tackle the problem. Lime uses a trained classifier, using sampling. Sharp uses game theory for the same purpose. Several comments. So Lime is you essentially sample the training data to train the simpler classifier. So it's very simple. Sharp, it has been shown that if you want to get the real values for Sharp, the accurate values for Sharp, it's extremely hard. For Anchor is really computes a set of literals, so it's an explanation as we see it. So it learns the features that are more relevant for the prediction. And like Lime, it is sample-based. Now, what we should note is that none of these tools has any formal guarantees of rigor in the way they compute explanations. So we decided to check what is going on. So the first question that we asked was, what is the overall quality of heuristic explanations when we compute? So if we compute them, let's assess them. So what we did was as follows. We learned a machine learning model. We used XBoost to learn boosted trees. And then we compute the heuristic explanation with any of the tools I just described. And then we used our technology to assess the quality of the explanation, whether it is a PI explanation or whether it's really an explanation or not. So we just as an example, we compute an explanation with Anchor. We check with our approach whether it's correct. If it is correct, we refine in case there are literals that we don't need. If it's not correct, we repair and propose a correct explanation. So by the way, here we use not neural networks, we use boosted trees, and at the time we showed that our approach using prime implicants scaled for a realistic sized boosted trees. So just as a very, very simplistic example. So for the zoo data set, which is very well known. So again, this is a very simplified boosted tree, just to illustrate the main points. And so as an example instance, if these features are true, then we are going to predict a reptile. Okay, again, how can we check this? It's easy, we just plug in the features here and see which of the trees we pick, which one gives me the highest score. And after this, we can run Anchor on the whole set, and it gives us, so it says that if not hair, not milk, not tooth, and not fins, then, well, we should pick reptile. Okay, so this is essentially, we can summarize Anchor by saying that the implicit rule is Well, if you have these features with these values, then you are going to predict reptile, or you should predict reptile. Well, the problem is that even in training data, we found an incorrect explanation. So there is an example in training data where that 4 literals are true, and we should predict amphibian and not reptile. So this suggests the type of flaws that we can have. So we ran the approach I just described, and the results were, in our opinion, pretty clear. So these are the percentage. We considered 5 data sets. These are the number of instances that we consider, and as you can see, for anchor, which is as I said, in the feature based, there are examples where we are above 99% incorrect explanation. So essentially any explanation that anchor produces, it's incorrect. And there are examples where they have redundant, but usually not very significant, with some exceptions. And we could only find a data set where the explanations are usually correct. Okay, so again, this suggests that the explanations produced by these REC tools should not be trusted. But again, you could say that we were just, notice that here we're just computing one explanation. We could just be very unlucky. Again, it's very unlikely, but we could be very unlucky. So what we did next was measure how often are heuristic explanations really consistent with the prediction. So here it's a little bit more tricky because we need to look at all points in feature space. So the only way we could do this was we need an ML model that we can encode as SAT, because then we can count the models. So we use binarized neural networks. And then we compute heuristic explanations with anchor. Again, we got similar results with Line and Joao. And then we use a model counter, actually in general, an approximate model counter, to assess how often the explanation is consistent with the prediction. And so these were the results we got also 2 years ago. So these are the predictions of anchor on 3 different data sets. And as you can see, in all cases, anchor is very confident, saying that it's 99% precise. We got pretty different results. So we used approximate model counting for the different data sets. And as you can see, so we tried different instances, 300 instances. And for most of them, the precision is, again, if you put it here, even here, you are quite below the 99% claimed by anchor. So the results really demonstrate that this 99% confidence should not be really trusted again. So again, this I think supports why we need formal explanations. And what I'm going to talk about next is what we have been doing to be able to compute explanations efficiently. So let me start with decision trees. So what people, for at least 2 decades, people have been saying that decision trees are interpretable. So actually, I even started the talk by saying that decision trees are interpretable. And so you could say, oh, of course they are interpretable, right? And the answer is yes, but not necessarily. So let me give you an example, explain what we are trying to say. So this is a decision tree, again, plus or minus classifier. And suppose you have this instance, so 1, 0, 1, 1, 1, 0, 1, 1, okay? So, so you could ask the question, okay, why am I predicting plus when I have 1, 0, 1, 1? Okay, essentially we can ask the question, okay, what is the PI explanation for the prediction plus, given that this is the instance? So is the question, otherwise, is 1, 0, 1, 1 really an explanation? So let me try to convince you that this is really not the case. So, so let's first look at feature 1, x1, and so let's allow it to take any value. So right now it takes value 1. Let's allow it to take value 0. So, and if we allow it, if we allow it to take value 0, can the prediction change? So notice that if we allow it to take value 0, because x3 and x4 are 1, we don't have a chance. It's going to predict plus again. So the prediction does not change. So this means we don't really need x1. And we can ask the same question. So does the prediction change if x2 and x1 can take any value? So now this is a little bit more tricky, because now we can allow x1 to be 0 or 1, and we can allow x2 to be 0 or 1. As you can see here, we don't even test x2, so that is not important. Here we can test x2, but when we test x2, it predicts plus again. So the answer is no again. So essentially, the PI explanation in this case is just x1 equals 1 and x4 equals 1. As long as this is true, we are going to predict plus, and the value of x1 and x2 are irrelevant. So what we proved actually at the end of last year is that there are functions for which there are pads in the decision tree that grow with the number of features, and the explanation is of constant size. And so this can happen in practice. So how do we compute explanations for a decision tree? Well, one way is to do what I just described. So we just encode everything and use an NP oracle, worst case exponential time. But in this case, it's actually simpler. So if the prediction is plus, like in this case, what I want to be sure is when I drop literals that I cannot get to minus, essentially. So I need to ensure that all the pads that go to minus remain consistent. So essentially what I need to do is to find a subset minimal hitting set of all the pads that predict minus. And so that hitting set is the set of features that I need to keep. And this is well known to be solvable in polynomial time. So again, we can use a dedicated algorithm, but the problem is that well known to be solved in polynomial time. Now you could say that, okay, this was a very concocted example and you never see this happening. And I'm going to convince you that is not the case, because most of the books that you have studied machine learning from have decision trees that have this problem. So if you look at Russell's Norvig book, so this is the standard, the well-known restaurant example, it's easy to see that for the decision tree they produce in the book, if the prediction is full, yes, tie, no, so no, you should not wait at the restaurant, the feature hungry is irrelevant. Okay, no matter the value you put on hungry, you're going to predict no. Okay, so, and I think there are more examples. If you don't like Russell Norvig's book, you can look at the tree ensembles book by Joao, and again, the same problem happens. So if you put 125, minus 113, so you go this way, right? No, you go this way exactly because it's not yes, and then you go this way. So what the value of x of y is really not important, because you are going to predict cross no matter what. If you prefer Alpaiden's book, the same problem. It's very similar actually. If you prefer the Schwartz Ben Davis book, the same problem again. It's just it becomes categorical, but it's the same problem. So if you predict not tasty here, then the attribute of color is irrelevant. And finally, Pula McWhorter's book has lots of examples of redundancy in the decision tree. So again, I think it's most of the books that people use these days for teaching, at least the decision trees. So you could, again, even if you're not convinced by looking at the examples in the books, we tried lots of data sets, and we tried two well-known decision tree learners, and we concluded that the number of pads that have redundancy is quite significant. So here 86, 80%, 73, 80. So, and by the way, IAI, it's a tool, commercial tool. It means interpretable AI. So essentially, you are getting pads that have lots of redundancies. Sorry, you are getting decision trees with lots of pads that have redundancies, and then this is actually the percentage of literals that are redundant, and it can be quite significant as well. And the ATI has been around for almost 2 decades as well, and you can see the percentage of redundant pads is also quite significant. And again, the percentage of literals in pads that are redundant can also be quite significant. So again, it can be important to find explanations for even for decision trees. So what we have been doing was essentially motivated by some of these results is asking, well, how can we compute explanations effectively, meaning efficient in practice? And we have now a bunch of results. So, so for different types of class of classifiers, we have shown that several are tractable. And for others, they are not tractable from a computational complexity point of view, but we showed that in practice, they are extremely effective. So we have shown that the decision random forests are hard computationally from a computational complexity perspective, but in practice that we can be very efficient. I'm going to show you a table shortly. And the same applies to decision lists, and boosted trees not so much, and that's why in terms of being effective or ineffective, it's right here. In terms of tractable classifiers, naive-based classifiers, we showed it last year. Decision trees also last year. Then we show that a large class of classifiers that can be mapped to what we call an explanation graph, like decision trees, OBDDs, OMDDs, all of this can be explained efficiently also. This month at ICML, we are going to explain how any monotonic classifier can be explained efficiently as well. So here it doesn't matter. So as long as the classifier is monotone, you can explain it in polynomial time. More recently, we show that a very large class of knowledge compilation languages can be explained efficiently, namely the NNFs. And this includes, for example, SDDs and so on. And we also show that special types of classifiers, which we call generalized decision functions, can also be explained efficiently. So again, this is all the ones we can explain efficiently. There are some that we cannot, like neural networks and Bayesian network classifiers. So there are still some open questions out there for sure. So in terms of random forest, again, I'm not very quickly try to summarize. So again, data sets, features and instances and classes. So again, we have a lot of variety, number one. In terms of the random forest, the depth that we considered for each class and the number of nodes that we were getting. And so notice that in terms of nodes in the random forest, we can get pretty large number of nodes. And the accuracy of the classifier. And so again, we just pick data sets for which we get a reasonable accuracy. The size of the forms that we're getting, by the way, this is pure propositional encoding, so we can use a sat-oracle. And the times that we got to get the explanations in total. And we decided to compare with Anchor, so one of the heuristic explainers that is extremely well known. And why did we do that? Just to show that even for a random forest, which is not tractable, so it's NP hard to explain, the average time is usually around one or more orders of magnitude faster than Anchor, which is heuristic. And again, there are a few outliers, but almost without exception, we are, for all the instances that we came across, we are faster than Anchor. Okay, so just the final topic is duality in explanations. So the type of explanations I covered during most of the talk were called adductive explanations, AXPs or PI explanations. So we want a minimal set of literals that is sufficient for the prediction, and this is yet another way to formalize the problem. So for any point in feature space, so again, my explanation is X. For if any point in, any feature is in the explanation is fixed, if all of them are fixed, and they keep the value, then the prediction remains the same. Okay, a contrastive explanation is a minimal set of literals that is sufficient for changing the prediction. So there is a point in feature space which, if the features that I'm not allowing to change are kept fixed, so I'm allowing the other ones to take any value, I'm able to change the prediction. Okay, and again, this can people call these contrastive explanations or counterfactual explanations. And what we showed is that they are related; they can be related. So there is a minimal hitting set duality between abductive and contrastive explanations. Again, to the best of our knowledge, this was completely new when we came across the result. So you could say, but why should we even care about this? And the answer is, well, several reasons. First, we can compute abductive explanations from contrastive and vice versa. That's number one. Number two, we showed in a number of papers that we can essentially enumerate the two concurrently. We need the two to be able to do enumeration, and we can enumerate the two concurrently. And more recently, a few months ago, we showed, and it's a paper that is going to be presented in November, we showed that we can use duality to prove that feature membership, asking whether a feature is in some explanation, is in polynomial time for decision trees. The only way to get to this result was to use duality. And again, so the result itself is new, but what we did is just to use the results of Reiter from the 80s. So that was one type of duality, very recent. Before that, we had a different type of duality we called global explanations, and that one we related with adversarial examples. So there is a vast body. There was at the time a vast body of work on computed explanations, heuristic explanations, but there was some recent, like ours and others. And there was, of course, a huge body of work on adversarial examples. Again, rigorous and heuristic approaches. And so the question that we asked ourselves was, can explanations and adversarial examples somehow be related? And there was at the time, this was 2019, there was some paper saying there seemed to be some connection, but really it had been elusive for most researchers. And so we show the first link between explanations and the adversarial examples like as follows. So we considered global explanations. And again, the explanations I spoke until now in the talk they are local because we use an instance. We work with respect to an instance. Global is just any prime implicant for the classifier, okay? And the counterexample are a set of features that I need. If I use those features, I can change the prediction. And so we showed in this paper that the global AXPs, so all of the prime implicants, are mean-weighting sets of the counterexamples and vice versa. And we also showed, again, it has to be, if you want an adversarial example, essentially you can work from a counterexample, because again, you are guaranteed to change the prediction. And again, this is also based on writer-sitting set law. Okay, so essentially what I did during this talk was to give you an overview of our work, which is at the intersection of automated reasoning and machine learning. And most of the work that we have done until now is on explainability. We have some results on learning and some results on fairness, but most of the results until now are on explainability. So we showed that we have an alternative to heuristic-based explanations. And again, we show that if, depending on the application, in some applications, of course, it doesn't matter, but if we are talking about high-risk applications, then heuristic-based explanations should be viewed with care. And so we showed that we can use formal methods to not only to define with rigor what an explanation is, but to also compute those. But of course, this is not the end of the story. So again, we have several results, several recent results, but there are lots of challenges still. So as I said, we can now do explanations very efficiently for several classes of classifiers, but there is still a problem. Of course, there will always be a problem. Right now, well, because neural networks and Bayesian network classifiers, we cannot yet explain it very efficiently. So this would be two challenges for the future. And even though we can do explanations efficiently, for example, for random forests, boosted trees, and so on, and even though the evidence suggests there is no alternative in high-risk settings, really, as far as, well, some people are using it, but yet there is no snowball effect of adoption. So we are still working towards having others using this technology. Thank you very much. And I will be happy to answer your questions.
Thank you very much, Joao, for your talk. Are there any questions? As far as I can see, there are a couple of them in the chat. Just wonder if people would be willing to ask them directly. We still have time.
Okay, so Roland Diap asked what would be the size of the PI explanation. Again, the size, I'm not sure exactly. So as I explained, we are computing either subset minimal or cardinality minimal. And so that we can, in the worst case, it can be as large as the number of features in the input. What we observe in practice is that it is usually not the case. And depending on the model, you can get pretty small explanations. So, but that is, of course, another area of research. Someone asked me,
is the number of them. Also the number of them.
Oh yes, that's a very good question. Yes, we have a paper at NIPS last year on naive-based classifiers, and we showed we could easily compute 1 million explanations. So that could be an exponentially large number of explanations depending on the classifier. So yes, that is another challenge. But again, we show that we can, of course, a human cannot go through 1 million explanations, but we show that we can enumerate those explanations in a matter of seconds. At least when we can do it in polynomial time, or when we can do it efficiently. But of course, another open question is how can we, is there a way to automatically analyze explanations? So that is open. There was another question. Yeah, well, Peter Stuckey asked, has anyone from the ML expression community reacted to the results? No, not really. But actually, I mentioned our results, but we are not alone anymore. So actually, I think we were the first ones to show that the explanations computed in machine learning were problematic. Right now, there are different groups claiming there are different types of problems with explanations, heuristic explanations. So I think it's pretty clear now that this is really problematic. Again, it depends, of course, on the application. We are concerned with settings where you need to trust. So, of course, if it's a setting where you can make mistakes or a small number of mistakes, again, it's not a big deal. If it's a matter of affecting human people's lives, then I would say, well, we should be very careful with the explanations we are computing. There was a question a long time ago from, can you give an example of an explanation using this formalization? I think I did. I think if you're talking about the neural network, eventually I did that. So I think I answered that question later.
Yes, I think that was the question.
Yes, yes.
Joao, I have a question. You mentioned that there are plenty of explanations, even for one instance, like millions or maybe more, maybe an exponential number. Is there any work on computing, say, preferred explanations or some explanations that makes more sense to a user?
Yeah, maybe you're asking the question because you know the answer. I don't. So I know that the complexity, as soon as you have a preference, the complexity most likely is as bad as finding a small explanation. So of course you can use heuristics again, and that I don't recall if we tried honestly, but if formally, so if you want to make sure that you give preference to some feature, that makes the problem usually much harder. So again, all the results I showed in terms of tractability are when you don't care, you just want a subset minimal explanation. So this, of course, for students interested in research topics, this opens a huge number of interesting research topics. Like, for example, we have now all these classes of tractable models for which you can compute explanations efficiently. Okay, what happens if we want to compute preferred explanations efficiently? Well, lots of questions to answer, yes.
Thank you. And as far as I can see, there is at least one question in the Vienna audience.
Yes, thank you. I have a question regarding the abduction approach. So basically you use logic-based abduction. So this means that your explanations basically are only literals, right?
Yes.
Wouldn't it, at least in some cases, make sense to also isolate the parts of the background theory that actually explain the results? So you actually also try to isolate the parts of the rules or the network that are actually responsible for the results you're trying to explain.
Very good. That's a very good question. Thank you. Very good question. So again, it's a matter of belief. So we believe that the model is correct. But of course, as you are hinting at, we can use this for debugging the model itself. Yes, we can. So actually, in model-based diagnosis, this is what people do. So if you know that for a given input, you should get some explanation, for example, then you could just dig in and try to understand what is failing in the model, for example. So yes, the answer would be definitely we can do that. I think there is you're welcome. There is another question. I cannot hear you.
Yes, thank you. Thank you very much for your talk. I have a question regarding that what you said for decision trees. Does this also applies for covering rules?
Yes, well, I think so. If I understand your question, I think so. We have. So I'll try to be rigorous in my answer. So the answer is we believe it is. We showed that. So the same type of rationale that we use for explanations that we need. So in terms of the need for explanations, the answer is yes. So if we need that for decision trees, and we will need it for other types of rules. In terms of the complexity is fairly different. So if we have order, so decision lists, this is what we call decision lists, then it's NP hard. If it's unordered and if you respect some conditions, which this is what we call the generalized decision functions, then you can explain them efficiently as long as the rules can be represented in NNF. DNNF. So so it's a class of knowledge compilation languages, and as long as you are below the NNF, then you can explain efficiently if it respects the criteria for a GDF. So what happens is that it depends on the type of rules that you are talking about. So if you have order, you are in trouble. If you don't have order, well, you are in general in trouble. But if you impose some criteria, then you can do it in polynomial time.
Thank you.
There is another question in the chat. Roland is asking if the redundancy in the T is simply because those are full trees. So if one uses multiple trees, then this goes away.
Well, they don't have to be full trees, number one. They actually, this is essentially it happens as long as you are trying to represent a disjunctive concept. So as long as you are trying to represent disjunctive concepts with decision trees, you are going to have this problem. And so it's not related with redundancy of the tree. It's inherent to the way you build a tree. Of course, if you want to do, if you have a more powerful language, then those types of problems, some of them will disappear, yes. But then you pay the price in terms of the cost of explaining. So, for example, if we are doing ensembles, well, the most simplest version of ensembles random force, we prove that it's NP-hard. So it seems there is no way around. The simplest is decision trees, but even decision trees, we need explanations, and we can explain in polynomial time. If you want some more powerful language, then you may pay the price in terms of explainability cost.
Thank you. Are there more questions? Okay, if there are no more questions, let's thank the speaker, and thank you, Joao. It was a great talk.
You're welcome. Thank you for the invitation.